Right, good morning. Any questions, any comments? Should I start? So I want to talk about finite potential. And hopefully we'll today finish this chapter and we'll start the next week. So we are trying to solve Schrödinger equation for given potentials, and our last example is V of x is equal to minus V naught if it's inside some domain, and 0 otherwise. Okay? And the picture is something like this. We have a well and we have to choose the energy, and initially I'm going to choose the energy to be here, which we called bound states, and then I'm going to choose it to be here, and hopefully in the second hour I also flip the potential, so this is minus V naught. We are also going to consider so-called barrier tunneling, and that will be the end of the chapter. Okay? So let's consider bound states. So I'll start with bound states, which is E is equal to 0. So this is x. This is x is equal to minus a. This is x is equal to a. So this distance is V naught. That means this point is minus V naught. This point is 0. And this one is energy which is less than 0. Okay, that's the geometry given to us. And what we need to do is solve Schrödinger equation. Let's do that for each domain. So here we have minus h bar squared over 2m d squared psi d x squared is equal to e psi. We know e is negative. If you forget that, you can take it inside absolute value and put a minus 1, but I'm not going to do that. And our trick is carry here and here, raise this, and move this a little bit here, and this is like that. We know E is negative, this whole constant is positive. Negative times minus 1 is positive. That means this entire coefficient is like a positive quantity, and I'm going to call it alpha squared. If you want, let me also write the definition. So this is 2m. Let me emphasize it's positive, not to confuse you. Good. And that means, okay, the solutions here are going to be some a times e to the minus alpha x plus b times e to the alpha x. Good. So I will do exactly the same thing in the second domain. So here we also need to add, let me write it from the beginning. So we need to add the potential minus h bar squared over 2m d squared dx squared psi plus, so this is actually minus v naught psi is equal to E psi. So I will carry this V naught to here. So this is V naught plus E. And I can erase this. And I know, like, you can see V naught, absolute value of V naught is bigger than absolute value of E. That means this V naught plus E is a positive quantity. So let me also move this to M over h bar squared. And lastly, there's this minus sign. So this is minus. Here you can see this entire quantity is now negative. So this is negative. And for that, I'm going to call it, I don't know, what did I call it here? Let me call it Q squared, which is going to be equal to 2m over h bar squared, V naught plus E.
I don't understand. V0 is negative value.
No, V0 is positive, minus V0 is negative. And this thing is right?
Okay.
Right?
So V0 bigger than E and
Exactly.
positive. Yeah.
Exactly. V0 is positive, E is negative. But since V0 is deeper than red, the picture, like I also got confused. The picture is telling me what it is. V0 is bigger than E, so this thing is positive. Okay? Yeah. And the solutions here are going to be, I used A, B. Yes.
Why Q squared is in square root?
Oh yes, that's because. Yeah. Thank you. So this is. I use A, B. We can use exponentials or sines and cosines. Choose whichever you like. They both work. So it's C sine QX plus D cosine QX. Good. And on this side, I have exactly the same solution here. Let me just copy. So nothing changes here. And here I am going to call it A, B, C, D. E is energy, I'll skip E. F, e to the alpha x plus G, e to the minus alpha x. Good. So this is the solution of the differential equation. Now we need to impose boundary conditions. The easy boundary conditions, as x goes to minus infinity, we want something finite here. Minus something times minus infinity is going to blow up. Therefore, I'll cancel this. And similarly, I'll cancel this here. Good. If you want, let me relabel the coefficients because it's kind of awkward to have to use middle of the alphabet. So now it's my A, B, C, D. Yes?
I think it's better to write minus and plus in front of the square for Q.
Here? But this is my Q, right? That's how I defined. So this entire thing is, if you want, let's write this Q squared. You are right. Yes. This way is better, right? So that you have e to the iq and e to the minus iq. Yes. Now here is a little exercise. You can think about this, and we'll have more to talk about it in the future. So this is exercise. Show that for v of x is equal to v of minus x. That means if the potential is even, solutions are either psi of x is equal to psi of minus x, or they are psi of x is equal to minus psi of minus x. Okay? So this is just like relabeling your Schrödinger equation and looking at the result. But you also don't have to do that. This just simplifies the algebra a little bit, but even if you didn't do that, things work out fine. Any questions? Now we will impose boundary conditions and eliminate arbitrary coefficients. So let's think about, can you see here? Good. So let's think about psi continuous at x is equal to minus a, and you can see it's like very easy to implement. A times e to the minus alpha a is equal to, okay, like that means, okay, so since this is the condition, I'm going to consider this solution b times sine qx and c times qx differently, because one is even, the other one is odd. So this is actually the other way. It doesn't matter. So this is even. So this is odd. And for even solution, this is going to give me, so this is even, odd. Even solution gives me a times e to the minus alpha a is equal to c cosine qx, and odd solution gives me a times e to the minus alpha x is equal to b times sine qx. Good. Because this is how I choose, right? I choose b coefficient in front of sine, c coefficient in front of cosine. I think I would, if it was now, I would choose the other way, but doesn't matter, right? B sine, okay, good. Can you speak up? Because I had the plus here, and the boundary is at minus a, right? That's a good point, thank you. So psi prime continuous at x is equal to minus a. So I am going to have alpha a e to the minus alpha a is equal to derivative of cosine is minus sine minus q c sine qx. Good?
X is equal to minus, it should be minus b.
Oh, yes. So this is, okay, yes, I didn't. So this is, sorry, this is a. So minus a is here, plus, doesn't matter. Here, this is, I put minus a, so I put minus here. Actually, let me emphasize this. So there's like a minus here. Thank you. Let me check. Yes, good. I think I have a typo here, but this is correct. And here I have sine minus a q, and I'll take this minus to outside, and I'll put this plus. I think this one is plus. I'll put red. If we make a mistake, we can come back and fix it at the end. And similarly here, a times e to the minus alpha a times alpha is equal to, and now derivative of sine is cosine, and this is going to be b cosine qa. Good? And you can see there is like one arbitrary condition. There is like a condition on D, and I will write it as like A is equal to D for even solutions and A is equal to minus D for odd solutions. Yes. This one? This one?
QB cosine QA.
QB. Oh yes, yes. There's like Q here. This one?
Yes, that was minus.
So let me check. So this is derivative is alpha A e to the minus alpha A. I think this one is correct. Is equal to derivative is derivative of sine is cosine. There's BQ cosine Q. I think this is correct. And this one is minus, like you said. That's also correct. Yes.
In the old is x power
Which line? This line? Here?
No, like at the old column, the first one.
This one? So I
The old
here, this side.
orada üstünden bulunan x var.
Oh yes, absolutely yes. So this is A. Okay, thank you. I appreciate. Good. We have 1, 2, 3, 4. If you want 5, 6 equations, yes.
I didn't understand why we omitted the minus by taking derivative of the odd.
You didn't understand why we omitted.
The minus. Because it's cosine, so
So this condition,
no, the odd one.
the odd this condition.
Yeah, it turns into cosine, so it's even, but we still omitted the minus of minus b.
Yes. So what I did is like here. So this one is I think correct, right? This is A times e to the alpha times minus A. This is correct.
Yeah.
On the other side, I have B times sine Q minus A, right? Because we are looking at, right?
No, that minus comes from the a, so that's why we have
Exactly. And I carried it out because I forget and he pointed out. And I think this is minus. I mean, it is like, I always make mistakes. That's why it's always good to be open and leave room to fix your mistakes. Yes.
Maybe there's something, but where's the negative in the derivative of that?
Which, negative from the derivative, where is it coming from?
Alpha A e to the minus alpha.
So let me number these equations. This is 1, this is 2, this is 3, this is 4. Which one?
So 4 is the derivative of 3.
4, derivative is, right?
So where's the negative in the derivative?
Well, let me check. So this is alpha times A times e to the minus alpha A is equal to, we are looking odd solutions. Derivative of sine is cosine. Even if you put minus here, cosine minus is equal to cosine plus.
Yes, so should there be minus outside? Carry from before?
But this is like, right? We start with sine, take the derivative is b cosine q x times q. And if you put x is equal to minus a, cosine plus is equal to cosine minus, I think there is no sign here. This is correct. Good. So what I will do is I will divide 2 by 1, and this is going to give me, let's see, so this factor will cancel, right? I'm going to have alpha is equal to, so there is like c's cancel, I have q times tangent qa. Good. And similarly, let's divide 4 by 3, and this is going to give me, okay, these guys cancel, alpha is equal to minus q, cosine divided by sine is cotangent q times a. Good? Yes. So this is like I am saying, like we need to choose either even or odd solutions. Like solutions, okay, inside there is like something like this. Outside, like let's think about the first one, right? So this one is even. That's why the coefficient here should be equal to coefficient here. That's how I write this. And let me draw like an odd solution. The odd solution is like something like this, right? So this one and this one, right? So if this side is coming from, right, psi of x needs to be minus psi of minus x, so that I need to have this extra minus sign. All right, so that's it, right? We solved the condition. So this gives us a condition, this gives us another condition. We now just manipulate these equations to make it a more palatable form, and then that will be the end of the solution. So let's define a z which is equal to q times a, and that means 2m over h bar squared v naught plus e, we know e is negative, times a is equal to z, and from here, like let's put this q here, this is q, so this is q, and I want to put minus sign here, this is cancelled. Now I need to find an expression for this alpha over q. So alpha over q is equal to this. Let me multiply both numerator and denominator with a, q times a, and this is going to be, alpha is like 2m over h bar squared e times a, divide this entire thing with this thing. And this is going to be equal to, what did I find? So this denominator is what we call z, right? So this is z, and here I want to okay, let me do it here. So this is my z squared is equal to v naught minus e divided by h bar squared over 2m a squared, and I want to write this as e divided by h bar squared over 2m a squared is equal to z squared. So I took this here. I think let me write it like this. So this is v naught divided by h bar squared over 2m a squared minus z squared. And here I want to call this object z naught. Z naught squared. Okay. Now I think this thing makes sense. So this is going to be root z naught squared minus z squared, and if I push this inside the square root, what I have is z naught squared over z squared minus 1. Good. So I have alpha over q, I have z. Now I can rewrite the equation. So I have this equation. So this equation is going to give me, so inside I have z, and alpha over q is z naught over z squared minus 1. So this one is even. And you can do exactly the same manipulation, right? If you look at above, you replace tangent with cotangent and put a minus sign in front. So I'll put here a minus sign and I'll make this tangent cotangent. So this is odd solutions. Good. How do you solve these equations? Any suggestions? Exactly. Let's forget about this for a little bit. Like suppose, I think I sometimes get confused about this. Suppose I want to solve something like this. Sine of x is equal to x cubed, right? So this is like a nonlinear equation. This one is so-called transcendental equation. And we cannot, use algebra to eliminate here, right? So what we can do is we can draw sine. So this is the sine. And we can draw this x cube. X cube goes like this here. And whenever these two lines, this side and this side intersect, this is a solution. There is a solution is x is equal to 0. There is a solution here, and there is a solution here. Good? So what I'll do is I'll plot this side, and I'll plot this side. Whenever they intersect, I'll call it a solution. So let me use it in Mathematica. Okay, so this is... So what we need to do is we need to plot two things. One is tangent z, and the second thing is some z naught squared divided by z squared minus 1. And let's, I don't know, it doesn't matter, let's draw it from z is equal to 0 to 10. And I also need to put something for z naught, and I'll do it with manipulate. Manipulate. And you need to put comma here and put z naught, I don't know, 0 to 5. Okay. Right now z naught is 0. We don't have a solution, but if we increase z naught little bit, you can see, so blue line is tangent, orange line is this square root, and as you increase z naught, this square root comes from minus infinity and intersects. And you can see as you increase, there's like one intersection, that means there's only one solution. Increase. You can see whenever I cross this threshold, I'll have one more solution. Now I have two solutions, one this, another one this, and I can keep increasing. Let me do this 10. Now I have the third solution, and if you keep increasing, and what is z naught? If you look at the equation, z naught is how deep the potential well is in units of this quantum energy, right? And as you increase the quantum well, you are getting more and more and more bound states. Good. And the question is, what if z naught is 0? Even if z naught is 0, you can see this orange line comes from minus infinity, right? This guy goes through 0. This guy comes from minus infinity and intersects the x-axis. That means even if z naught is infinitely small, they have to intersect at least one time. Okay? So that means there's at least one bound state. Let me try to. So this is at least one bound state. Let's do exactly the same thing for the other solution. I'll just copy and change. So what was it? Tangent was cotangent, and there was like minus here. That's all we have, right, for the solution. And now you can see, right, compare it with this, right, tangent turned into cotangent. It's not, yes. At least one bound state means no matter how shallow your well is, even if your well is like tiny, like infinitely narrow, there is still one bound state. And that's like a quantum result, right?
But do you mean that if V0 goes to 0?
Yes, as V0, or in a more like meaningful way, you need to take something with dimension go to 0. As V0 over this quantity goes to 0, you still have one bound state, no matter how shallow your potential well is. But there is nothing to understand. The solution is telling us this, right? Like I came here.
Yes, but over there, when we first bounce happens, it's not 0. Z0 is not 0.
But orange line, yes, Z0 you can take as small as you want, right? Like let's take Z0 is equal to a smaller window. Now, as soon as Z0 is infinitely small but non-zero, this orange line and blue line will intersect. You need to zoom in here, and no matter what you do, this intersection cannot be eliminated.
So it's coming from infinity.
Yes, it comes from infinity. Yes, yes, yes. So something goes to 0 here, something comes from infinity and intersects the x-axis. There is no way these two lines do not intersect. Whereas the other one is not like that, right? The other one here, so I increase. Now it doesn't come from minus infinity. It comes from, it doesn't come from plus infinity. It comes from minus infinity, and it stops at the x-axis. But to have a solution, I need to increase all the way to here. Now I have a solution. Okay, and I keep increasing. Now I have a second solution. Good. So let me write this. Even solutions. I think I also had like a condition here. You need to have this Z0. You can see Z0. So this is 0. I think this is pi. I think this right the middle is pi over 2. Z0 needs to be bigger than pi over 2 for this solution to exist. Okay, this is odd solution, sorry. Z0 should be bigger than pi over 2, and this gives you a condition for V0. V0 should be bigger than h bar squared over 2m a squared pi squared over 4 for at least one solution, whereas even solutions exist at least one, let me say it this way, at least one even solution as V0 over h bar squared over 2m a squared goes to 0. Okay, this is a famous result. Everybody knows.
Can be Z0 equals to pi over 2 for at least one solution. We write on the bigger than. We put equals to.
Yes, if you want, you can put equal to. Right. As soon as they are equal, they start intersecting. That's correct. Yes. Yes.
Where did you decide? How did you decide on the pivot?
Because so this is cotangent. So cotangent diverges at x is equal to 0, and cotangent diverges to minus infinity at x is equal to pi, and the middle point is pi over 2.
But mathematically, if you were in the exam, you won't have mathematical. So you won't be able to check it.
I mean, it's okay. even if you have a mistake, right? Suppose you have a mistake and you said not pi over 2 but pi, right? There is something here.
There's supposed to be some
Right.
duration of that from the
Yes.
equation, right?
Yes.
But was the condition, what does this condition imply in terms of the equation that we had? And
This condition,
yes, what happens if we do not obey this in terms of the equation? Not
then you don't have a solution. We say that there is only one solution and that solution is even. There is no odd solutions. Right? There's always at least one solution which is even, but as you increase the depth of the well, you have more and more solutions. And like sketching this, like right tangent and cotangent, it takes a little bit thinking. Don't worry about it. But this thing you can remember, right? Like this, no matter how shallow your well is, there's always a bound state. That's the important result. We should remember. Also, you can see if I increase V to arbitrarily, right? As this thing goes to very deep, okay, this is, let me call it 10. Now, as you can see, there's like more and more and more solutions. And they more or less intersect where this tangent diverges, and tangent diverges at n times pi. And from here, okay, let me write this condition too and finish it there. Zn is equal to n times pi, and also do it for, so this is for even, exercise for odd, right? Think about how this changes, and this is going to give you E is equal to h bar squared over 2m a squared pi squared n squared minus b naught. And this is making sense, right? As the potential goes to deeper and deeper, it should turn into infinite potential, and we know what infinite potential does. It has infinitely many states. That means you just start filling the states until you reach the rim of the well. After the rim of the well, you don't have any bound states. Good? Any questions? So if not, I will turn into scattering states, and that will be the end of the lecture for today.